Hello everyone, I'm Himanshu Vasnani from Department of Mechanical Engineering and I'm here to discuss with you on the subject non-destructive and evaluation and testing, and today's subject code is ME419, unit number 5 in the series, lecture number 33. Okay, today's topic are principle and theory of eddy current inspection, overview of signal detection, processing and display. So, the learning objective for today's lecture are to provide the students with a basic understanding of principle and theory of eddy current inspection, to know about the signal detection, the processing and display in eddy current inspection. A learning outcome after the lecture will be the students will have an understanding of principle and theory of eddy current inspection, and students will understand signal detection, processing and display in eddy current inspection. So let's start with the topic. First of all, principles and theory of eddy current inspection. See, we have been studying about the eddy current inspection in the previous lecture, where I gave you a short introduction of how the eddy current inspection is done and in which materials it is suitable, like in ferromagnetic materials it is suitable. And secondly, what variables are responsible for what variables are responsible for eddy current inspection. So let's start with the new that principles and theory of eddy current inspection. Now, in induction of eddy currents, they say that as the electromagnetic field from a coil penetrates a conductor, it generates eddy currents parallel to the surface of the part and at right angles to the direction of the applied field. Okay, and you can see in this figure, okay, the frequency of eddy current flow is the same as the electromagnetic fields. So when we talk about this thing, you can see in the diagram, on the upper diagram, you can see that there is a primary magnetic field shown. Okay, and you have a test coil from which AC is given, and then you have the eddy currents. Okay, and there is also a secondary magnetic field working on that. Okay, if you see in the bottom diagram, you also can see that there's a primary magnetic field shown with the arrow, and also there's a secondary magnetic field shown in the arrow. You can see the arrows or the direction of both the things of primary magnetic field and secondary magnetic field. Okay, and there is in the center you can see the eddy current. It is shown with the arrow. So in this way, you can see in the diagram the nature of different magnetic fields, primary and secondary magnetic fields. So the primary magnetic field, let's discuss about it. The primary magnetic field is the coil's magnetic field. Okay, this field is called electromagnetic because the magnetic field is produced from electricity rather than from a permanent magnet. Okay, now the rate at which the electromagnetic field varies is called frequency, and the strength of the electromagnetic field at the surface of the conductor, it depends on the coil size. Okay, it depends upon the configuration, the amount of current through the coil and the distance from the coil to the surface. So these factors are very important that for determining the strength of the electromagnetic field at the surface of the conductor. So the strength of the electromagnetic field at the surface of the conductor, it depends on the coil size, coil configuration, the amount of current through the coil, and the distance from the coil to the surface. So the amount of eddy current and the amount of eddy current the primary field is able to generate is dependent upon properties of the part under test, that is the workpiece, and the strength of the secondary electromagnetic field that opposes the primary field. Okay, eddy current the primary field is able to generate, okay, is it dependent upon first of all the properties of the part under test, that is the workpiece, and then the strength of the secondary electromagnetic field that opposes the primary field. Okay, so these factors need to be considered. Okay, now secondary electromagnetic field. Ah, the eddy currents also generate an electromagnetic field in the part. Okay, and this field called the secondary electromagnetic field opposes the, okay, and is a consequence of Lenz's law. Okay, we have a new law that is being introduced known as Lenz's law, and they say that Lenz's law, as applied in this case, states induced currents, that is eddy currents, act to reduce the magnitude of the inducing current. The opposition of the secondary field to the primary field decreases the overall electromagnetic field strength and reduces both the current flowing through the coil and the resultant eddy currents. So any changes to the properties of the inspection article produces changes to the eddy currents and thus their secondary magnetic fields. So in this manner, changes in the inspection article produce effects that can be detected by monitoring either the source of the primary electromagnetic field or the overall electromagnetic field. Okay, so for now we have discussed about primary electromagnetic field and also we have discussed about on what factors does the strength of electromagnetic field depends upon. Okay, and also we have also discussed about the amount of eddy current the primary field is able to generate and on what factors does it depend. Secondly, we have also discussed about secondary electromagnetic field and this principle and also the Lenz's law, which is working in this area. Now, the depth of penetration. Now, the intensity of eddy currents decreases exponentially with depth in a material. The intensity at any depth is affected by the same variables that influence the surface intensity of eddy currents, although not always in the same manner or by the same amount. Okay, to put it another way, the depth of penetration of a specific intensity of eddy current is affected by the variables. So here it looks into it comes into picture that the depth of penetration of a specific intensity of eddy current is affected by the variables. Generally, any parameter that increases the depth of penetration would increase the detectability of discontinuities deeper in the part. Obviously, if you want to find an effect, and if you have any parameter that is increasing the depth of penetration, obviously it will help you to detect the discontinuity deeper in the part. Okay, that is unique. Now, standard depth of penetration. What we just studied before is the depth of penetration, and they say that the intensity of eddy current it decreases exponentially with the depth in a material. But now we are talking about standard depth of penetration. Now, to say that three of these variables like conductivity, relative magnetic permeability, and frequency these are used to define the standard depth of penetration. These are used to define the standard depth of penetration. What are the three variables? Conductivity, relative magnetic permeability, and frequency. Now, standard depth of penetration is the depth below the surface of the inspection article at which the magnetic field strength or the intensity of the induced eddy current is reduced to 36.8% of the value at the surface. Okay. Now, since the depth of penetration is related only to a percentage of the surface field, that is the eddy current, surface field strength, that is the eddy current intensity, some test variables are not included. Okay, like coil configuration, size, current, and magnetic coupling, they are not considered. Okay, what they say? They say that since the depth of penetration that we have just discussed few seconds ago it is related to only a percentage of surface field strength. Okay, it is related to only percentage of surface field strength that is given. Okay, so some test variables these are not included. Test variables like coil configuration, the size, the current, and magnetic coupling these are not considered in this. Okay, these variables affect the absolute magnitude of eddy currents at a specified depth, but not the standard depth of penetration. Okay, these variables these will be helpful, but they affect only the absolute magnitude of eddy currents at a specified depth, but not the standard depth of penetration. Okay, now effective depth of penetration. We say that the effective depth of penetration is the depth in the inspection article at which the magnetic field or the intensity of the induced current is reduced to 5% of the value of the surface. This depth is approximately 3 times the standard depth of penetration. Okay, and they say that the effective depth of penetration is used to determine the test frequency when working with thin materials. Okay, so this effective depth of penetration, this is helpful to determine test frequency when working with thin materials. So the overall electric field does not extend beyond the back surface of the test part. So thickness variations effects can be suppressed. Okay, so effective depth of penetration is very helpful. That is used to determine the test frequency when working with thin materials. Okay, so now temperature and depth of penetration. Okay, the temperature is also very important because we know that it is helpful in some way that we will discuss earlier also, and the coming slide also we will discuss about that. So temperature and depth of penetration. For most applications, the temperature is not a major factor in determining depth of penetration. Okay. However, if necessary, effects of temperature would be included as adjustment to the values for conductivity and relative magnetic permeability. Okay, using the formula to calculate the standard depth of penetration. Now you can see in this diagram there is a primary secondary magnetic field in eddy current testing. So I have seen this diagram before also with you. You can see the primary magnetic field and the secondary magnetic field, and you can see the arrows how they are working. Yeah, you have seen the inspection part on the bottom side. It is given, and there is the eddy current flowing, and you can see the test coil. Okay, this is simple a diagram showing the primary and secondary magnetic field in eddy current testing. Okay, now the impedance. See, these terms are important when you study about eddy current testing because these terms are somehow helpful to understand this testing technique better. So, impedance is the total opposition to the flow of current represented by the combined effect of resistance, inductance, and capacitance of a circuit. Okay, what this impedance is the total opposition to the flow of current represented by the combined effect of resistance, inductance, and capacitance of a circuit. Sensitivity, another new term. Now, the ability of an eddy current instrument to detect small variations in test coil impedance is a measure of its sensitivity. This quality is interrelated with the properties of the test coil and the operating frequency. Therefore, instrument sensitivity to a particular flaw condition or material property shall be established from reference standards towards this condition. Okay, so just understand one thing, that sensitivity, it is the ability of an instrument that is used in eddy current inspection to detect small variations in the test coil impedance is the measure of this sensitivity. Okay, now resolution. Now the ability of a test system to separate the signals from two indications that are close together is defined as resolution. Now this property, this plus sensitivity must be considered in every flaw evaluation situation. Now probe designs, test frequency, and instrumentation design, these all factors are considered in determining the resolution of an eddy current system. Okay, now resolution obviously is really important because it is giving you the ability to separate the signals from two indications. Okay, those indications that are close together. So it is obviously very important when you go with the sensitivity part also, because this property plus sensitivity, this must be considered in every flaw evaluation situation. Okay, apart from them also, like crop design, test frequency, and instrumentation design, these are also supportive in determining the resolution of an eddy current system. Now, the measurement of resistivity. Now, electrical resistance is a measure of the resistance to the flow of electric current in a conductor. What is it? Electrical resistance, it is a measure of the resistance to the flow of electric current in a conductor. That we all know. It's now resistance depends on the length and area of the current path and the conductivity of the conductor. Now resistance is commonly measured in ohms. If a material allows 1 volt, okay, that's the electric potential of driving force to push 1 ampere of current through a conductor, the electric resistance of the conductor is determined as 1 ohm of resistance. Okay, they say that this is now defining the value of resistance. So they say that first of all, the resistance it depends upon the length and obviously the area of the current path. Okay, and the connectivity of the conductor. These three factors are important. Then they say that this resistance it is measured in ohms, and they say that if a material it is allows only 1 volt of driving force to push 1 ampere of current through a conductor, so the electrical resistance of the conductor is defined as 1 ohm of resistance. Okay, now this resistivity is a material parameter independent of the size of a material sample and is related to the resistance. So resistivity is defined as ohms times cross-sectional area divided by unit of length. Okay. Now measurement of conductivity. Now electrical conductivity is the reciprocal of electrical resistivity because we know that conductivity is flow and resistivity is opposition. So electrical conductivity is reciprocal of electrical resistivity. So the reciprocal of ohm is called as MHO, mho. Okay. So conductivity is commonly expressed in the units of mho per unit length. Like they say that in the resistivity is defined as ohm times cross-sectional area divided by the unit of length. So here the connectivity is commonly expressed as units of mhos per unit length, such as MHO per inch or MHO per meter. Now overview of signal detection, processing and display. Okay, now this is also really important when we talk really discuss about eddy current inspection because obviously the signal detection is a very important activity. How do you process those signals is also very important, and the display that we use to find out the exact results. So obviously is also very important. So just giving you a short overview of signal detection, processing, and display in eddy current inspection. Now signal sources. So when performing an eddy current technique, okay, the materials changes can be detected by monitoring the alternating current in the coil. Okay, like a single coil arrangement, or using a separate sensing coil to monitor the resultant electromagnetic field. Okay, or using a separate sensing coil to monitor the resultant electromagnetic field. Now, these signals can be analyzed for information relevant to the inspection being conducted. This is an important thing. The important thing to note is the coil that is acting as a receiver is producing an electric current that either leads or lags the instrument's oscillator current. Okay, the coil that is acting as the receiver is producing an electrical current that either leads or lags the instrument oscillator current. So the difference in this leading or lagging is the phase angle. What is this? It is the phase angle. The difference in this leading or lagging is called as phase angle. Now signal detection will go that now you can see the simple but effective signal detection technique is to use bridge circuit as illustrated in this. See, bridge circuit is obviously a very common, you can say, style of you can say signal detection technique. Okay, so here we are using again, and with the current flowing through the test coil and the coil position on a flaw free or reference area, the variables impedance Z can be adjusted so zero current flows through the amplifier. And this adjustment is termed as either balancing or nulling the bridge. Okay, what is nulling? They say that when the with the current flowing through the test coil and the coil position on a flaw free or reference area, the variables impedance Z can be adjusted so that zero current flows through the amplifier, and this adjustment is either termed as balancing or nulling the bridge. So you can see in the simplified bridge circuit on the right hand side, you have AC supply on the left hand side, and then you have test coil on the right hand side. And in between, you have this amplifier in the between with the Z1, Z2, and Z3 coming with you. Now, when the coil is placed on a flawed or damaged area, the resultant change in current through the coil unbalances the bridge. Okay, the resulting change in current, what it do to the coil, unbalances the bridge, and the current flows through the amplifier. Now, this current is the inspection signal. Okay, when the current flows the amplifier due to the, you can say, disbalancing or unbalancing of the bridge, and this current is the inspection signal. The signal has the same frequency as the current through the coil. So the phase and the amplitude of this signal contains information on the condition that caused the bridge unbalanced. Now, in the simplest type of instrumentation, like when you go for the signal analysis, they say that in the simplest type of instrumentation analysis of the signal, it consists of measuring the change in magnitude of the current flowing through the bridge. Okay, now changes in the magnitude of the alternating current are amplified and converted to a direct current for display or readout. So in more sophisticated instrumentation, both amplitude and phase are measured. Okay, how does the analysis? Changes in the magnitude of the alternating current are amplified and converted to a direct current for display or readout. So they have this both amplitude and phase, they both are measured in this. And now the display, the method by which eddy current signals are presented as dictated as the type of information required and the complexity of the instrumentation. These both things are important. Information required and then the complexity of the instrumentation. So when only signal amplitude is measured, meters, alarm signals or recorders are commonly used. Okay, when only signal amplitude is measured, then meters, alarm signals or recorders are commonly used. When both amplitude and phase information are to be displayed, a two-dimensional device displays commonly used. Okay, so these have. Now this was the diagram that I just shown you in the previous slide also. This is for information that is a simplified with circuit. Now amplitude display. Now meters may be analog or digital. Okay, we have seen this analog and digital in our labs also. So audible or visual alarms may be set to trigger when the signal amplitude exceeds a predetermined threshold. A recorder presents a continuous record of the signal amplitude during the inspection for subsequent analysis. Okay, now impedance plain display. Now, when you talk about amplitude display, obviously we know that we have different types of meters. The most common are like analog or digital display meters. Okay, so they say that when audible or visual alarms, this may be set to trigger when the signal amplitude exceeds a predetermined threshold. Then obviously a recorder is there which presents a continuous record of the signal amplitude during the inspection for subsequent analysis. Now, this there's an impedance plane display. They say that the defects or various or other variations in material characteristics will alter the strength and distribution of an induced eddy current flow. Now, changes in the eddy current flow will result in changes in the inducing coil. What do you do? Changes in the eddy current flow will result in changes in the inducing coil or sensor coil currents. These changes, this can be expressed as an apparent change in the coil's electrical impedance. Okay, now this makes it possible to associate changes in the material properties with specific changes in the apparent impedance of either the excitation or sensor coils. The two-dimensional display that permits this is the only most commonly used and is called as impedance plane display. Okay, this is how the display is there. Now, when we have the display with us, when we have this amplitude display with us and impedance display with us, then obviously we should go with the impedance changes. Okay, there should be information about impedance changes. So we say that the impedance of a coil it appears to change when it is placed adjacent to an electrically conductive or ferromagnetic part. Okay, when it is placed to an electrically conductive or ferromagnetic part. So the secondary electromagnetic field created by the induced eddy current in the part opposes the primary field. The secondary electromagnetic field created by the induced eddy current in the part opposes the primary part. This opposing field also induces a current flow in the coil in opposition to the primary current. This opposing field also induces a current flow in the coil in opposition to the primary current. So if the part is not ferromagnetic, the net magnetic field resulting from the combination of the primary or secondary coils is decreased in magnitude, as is the current flow in the coil. This is equivalent to decreasing the inductance and increasing the resistance of the coil. Okay, because obviously this is doing something, so it leads to decreasing the inductance and increasing the resistance of the coil. And if the part is ferromagnetic, the net magnetic field is increased. Now it is going the other way. Okay. Now the other way is that if the part is ferromagnetic, the net magnetic field is increased because of the magnifying effect of the relative magnetic permeability. But the current flow in the coil is decreased because of the opposing effect of the secondary magnetic field from the induced eddy currents. From the induced eddy currents. So this is equivalent to increasing both the inductance and the resistance of the coil. Okay, so in this manner, changes in a part that affect either the strength of the magnetic field at the surface of the part or the strength and distribution of the eddy currents in the part, it changes the apparent impedance of the test coil. So these variations in current flow, both phase and amplitude, can be detected with amplified, displayed, and analyzed as eddy current test results. The amplitude and the phase changes in the signals can be related to changes in the parts inspected. Now we have discussed about the impedance. Obviously, impedance changes, and the both cases are discussed when if the part is not ferromagnetic. So what will the effect of net magnetic field? And if the part is ferromagnetic, then what will be the effect on the net magnetic field? Now let's go with the impedance of a coil. So inductance of a coil. The inductance of a coil it depends upon the number of turns in the coil, the size of the coil, the permeability of the material within the coil, and the total magnetic flux through the coil. Okay, now these the factors on which the inductance depends. It is the turns, number of turns in the coil, the size of the coil, the permeability of the material within the coil, and the total flux within the coil. Okay, so the formula is like N is equals to N phi upon I. So where actually is the inductive resistance in ohms, phi you have the value 3.14, F is the frequency and L is the hertz. Okay, L is the in you can say inductance in the Henrys. Okay. Now, inductive reactance, the measure of the amount of opposition or resistance ohms to alternating current flow due to the inductance of a coil is called as inductive reactance. Okay, and inductive reactance is dependent upon the value of inductance of the coil and the frequency of the alternating current. And the inductive reactance increases as the inductance of frequency increases. So this can be stated as XL is equals to 2 pi FL, where XL is inductive reactance and pi is 3.14, F is the frequency, L is the inductance. So you can see the inductive reactance results from the electromotive force generated across a coil by the alternating current. The instantaneous value to this induced voltage increases and decreases as the rate of change of the applied alternating current decreases. Okay, this instantaneous value of this induced voltage it increases and decreases as the rate of change of the applied alternating current increases and decreases as shown in this figure. You can see in this figure you have the alternating current. Okay, you have it is starting. You can see how it is starting, and then you have the induced voltage. See, it has a different starting point. So you can see the horizontal axis having the time as a variable and amplitude is shown on the vertical axis. So there is approximately a 90 degree shown in this angle. Okay, and then you can see the different angles having like 360 degree, 180 degree, and 90 degree. Now the voltage is at its maximum value when the rate of current change. What happens? The voltage is at its maximum value when the rate of current change is at its maximum. Now this occurs when the current value is zero. Okay, this occurs when the current value is at zero. So conversely, the voltage is zero when the rate of current change is zero. And this occurs when the current is at its maximum value. Okay, so consider in 360 degree to be one complete cycle as shown in the diagram. The induced voltage leads the current, example that is out of phase with the current by 90 degrees. Okay, they say that consider 360 degree as one complete cycle. The induced voltage leads the current by 90 degrees. Okay, now the induced voltage is in opposition to the electromotive force applied to the coil, reducing the amplitude of the resultant current. So you can see this sinusoidal variation of alternating current and the induced voltage in a coil. Okay. Okay, the combining out of phase quantities. Now this is also really important because here obviously the values of impedance or resistance and inductive reactance, these all you can say are important and are considered while making this phase quantities. So combining out of phase quantities, when we say that the real coil has a resistive component of the impedance in addition to the inductive reactance. So they can be combined to describe net impedance. The coil can be considered to be a resistor in series with an inductor. So applying an alternating current to the series circuit will result in two voltages, one across the resistor and another across the inductor. So whenever you apply alternating current to the series circuit, obviously it will result in two voltages, one across the resistor and one across the inductor. So the net voltage across the combination of the resistor and inductor will be the combination of the two voltages. Now the voltage across the resistor will be in phase with the current, while the voltage across the inductor will lead the voltage across the resistor by 90 degrees. Okay, the voltage across the resistor will be in phase with the current, while the voltage across the inductor will lead the voltage across the resistor by 90 degrees. So the combination of these two voltages is shown in this figure. It results in a voltage will be out of phase with the current, but not by a full 90 degrees. Okay, you can see this diagram in the commanding out of phase voltages of this. Now XY plot representation. Now this is also very important because it is giving you another way to illustrate the combination of out of phase quantities in a coil, and you can see it in the figure also. Okay, you have on the horizontal axis you have the voltage drop and resistance Q. Okay, and then on the vertical axis you have voltage drop inductor. Okay, so you can see in the bottom you have the values of VR and VL shown on X and Y axis, and then you have a phase angle by phi it is shown. And in the center you have the resultant voltage drop point is coming teaching till is shown with the arrows at point A. Okay, now they say that another way of illustrating the combination of out of phase quantities in the coil is shown in this figure. Here the two voltages drop, one across the resistor VR and another across the inductor VL are plotted at right angles to each other. Okay. Now this represents the two quantities being 90 degrees out of phase. And this combination of these two quantities is represented by a diagonal line OA. You can see the line OA. That is the resultant voltage drop. And that is at the angle theta. Okay, with respect to the voltage drop across the resistor. So you can see this diagram that is showing relationship of voltage drops across the coil resistance and coil reactance. Now impedance plane representation. Just as the two voltages can be combined to produce the net voltage across a coil. Okay, I'll show in a figure. The resistance and inductive impedance its components can be combined to produce the net impedance of a coil. Okay, let me show you this diagram. This is a figure 4.10. It is showing the vector diagram showing relationship between resistance, reactance, and impedance. So you can see on the horizontal axis you have resistance that is shown in R in ohms, and on the vertical axis you have inductive reactance that is also in ohms. So you can see that there is a phase angle of theta shown, and with the line OA showing the impedance Z. Okay, so you can see that this is the vector diagram that is showing the relationship between resistance, reactance, and impedance. Okay, now this is the figure 4.11. Okay, now this is showing you the relationship of voltage drops across coil resistance and coil reactance. So on the horizontal axis you have the value of VR, and on the horizontal axis, sorry, on the vertical axis you have VL, that is voltage of inductor, and on you can see this angle theta, and on the angle theta you have this line OA. It is showing the resultant voltage drop. So they say that the resistance of two voltage can be combined to produce a net voltage across a coil, and the reactive and the resistive and the inductive impedance components can be combined to produce the net impedance in the coil. So what? The resistive and the inductive impedance components can be combined to produce the net impedance of a coil. Now in the figure that I've just shown you just now, the inductive reactance XL is plotted on the x-axis and the resistance R is plotted along x-axis. Okay, now these two values is define the impedance that is represented by the vector OA, and the value of the angle theta for the net impedance is same as the angle theta that is shown in the figure for the net voltage. This is important because it shows that the impedance of a coil can be displayed as the combination of out of phase voltage drops. Now, the amplitude of the impedance may be determined from the known values of resistance and inductive reactance according to the formula. So now the formula is like Z equals to XL square plus R square under root. So here you can see that the Z is the impedance magnitude in ohms, then XL is the inductive reactance in ohms, R is the resistance in ohms, and X is the capacitive reactance magnitude. Okay. Now typical values of an impedance diagram. Okay. Now you can see this impedance diagram. Let me show you the diagram first. Now you can see this diagram coming impedance diagram illustrating effects of variable connectivity. So you have this. You can see that there is a high connectivity metal at the bottom, and when as it is going up, it is giving you an impedance curve. Okay, and this is kind of an imaginary line. Okay, now it is helpful when the lift off traces are drawn. Okay, and you can see that there is a low connectivity of materials there. So in the bottom you can see you have high connectivity materials, and in the upper side you have low connectivity of materials. Okay, and through this you draw kind of an impedance curve that is the imaginary line. Okay, and this is showing the effects of variable connectivity. Okay, now this is giving you a conductivity curve that can be used to measure the relative activity of an unknown material by comparing the position of its indications on the conductivity curve to the position of indications from known. Now you also know that the lift-off lines are in different directions that the conductivity line. Okay, now changes in conductivity and lift-off are said to have different phase angles. And this phase angles you can I will also show you in the figure again in figure 4.5. Now the lift-off curve can also be used to measure the thickness of a non-conductive coating in our conductive surface. This is done by comparing the length of lift-off line for an unknown coating thickness to the length of the lift-off lines for known thickness. Okay, this is figure 4.15. It is showing the phase angle difference between line off and conductivity. You can see that there is a phase of angle between lift off and conductivity. So this angle is also very important, known as phase angle. Now thickness variations. Okay. Now this when the part thickness is less than the effective depth of penetration of the best coil of the test coil at the inspection frequency employed. The impedance curve departs from the connectivity curve as shown in this figure. Okay, now typically there is an increase in the resistive component of the impedance with thinner parts as compared to parts that have thickness equal to or greater than the effective depth of penetration. So as the thickness of the parts increase and approach more closely to the effective part of penetration, the curve tends to spiral as it approaches the end point, that is t is equals to 1, uh, that on the connectivity curve, where t equals the ratio of the specimen thickness to the effective depth of penetration in that specimen. What they say, t equals the ratio of specimen thickness to the effective depth of penetration in that specimen. Now you can see there is a t equals to 1 shown in this diagram. Okay, in the center of the curve you can see. Now you can see that there is an increase in connectivity when you go downwards, and as soon as the thickness is also increasing there. So you have different values of t. They are available like 0.10, 0.15, 0.20, 0.25. Okay, and there is a connectivity line also available when you at some point like zero point 0.4 on the vertical axis you have zero liftoff. Okay, so this is a kind of a curve that is showing you impedance diagram, showing the effect of specimen thickness. Okay, now conductive layers. Now the impedance curve for thin conductive layers on a substrate of different activity is also presented as a change in the impedance curve conductivity. Now the impedance for the layered material departs from the conductivity curve at the value corresponding to the substrate connectivity and forms a loop that rejoins the connectivity curve at the connectivity of a metal in the outer layer. So increasing thickness of the outer layer corresponds to a clockwise direction along the loop, and the point at which the loop rejoins the curve it represents the effective depth of penetration in the coating. Okay. Now let's discuss about the MCQs now, because MCQs are also very, you can say, should be studied very early. Okay, now the first question is that in eddy current inspection, now three of these variables like connectivity, relative magnetic permeability, and frequency, these are used to define a standard depth of penetration. Now, what do you think? That is it true or false? We have studied in previously in ECI that these analytical inspection, obviously three variables. These are very important that define the standard of penetration. Like, okay, the variables like connectivity, electromagnetic permeability, and frequency, these all are important. Okay, and they help you to define the standard depth of penetration. So this is true. That is, in ECI, Eddy inspection, three of these variables, connectivity, electromagnetic permeability, and frequency, these are used to define the standard depth of penetration. So this is true. Now the standard depth of penetration is the depth below the surface of the inspection article at which the magnetic field strength or the intensity of the induced eddy current is reduced to 36.8% of the value expected. It is true. Okay, we have true. Is the depth in the inspection article at which the magnetic field strength or the intensity of the induced eddy current is reduced to 5% of the value of the surface. Now this depth is approximately three times the standard value, standard depth of penetration. I think it's true. It's true in this case. Okay, this depth is approximately three times the standard depth of penetration. So it's true. This depth is approximately three times the standard depth of penetration. Now, the effective depth of penetration is used to determine the test frequency when working with thin material. So the overall electromagnetic field does not extend beyond the back surface of the test part so that the thickness variation effects can be suppressed. Now it is true in this case. Okay, true. Now the depth of penetration to a specific intensity of eddy current is affected by the variable. Generally, any parameter that increases the depth of penetration would increase detectability of discontinuities deeper in the path. Okay, so I think it's true in this case. The amount of, you can say, eddy currents, okay, in the primary field is able to generate is dependent upon the properties of the part under test and the strength of the secondary electromagnetic field that opposes the primary field. Okay, that opposes the primary field. So it is true in this case. It is true. The answer is A. The generation and detection of eddy currents in a part are largely dependent on the inspection system, the material properties of the part, and the test condition. It is true. Now, the strength of the electromagnetic field at the surface of the conductor it depends on the coil size, the configuration, the amount of current through the coil, and the distance from the coil to the surface. So I think it's true in this case. True answer is true. Now, as the electromagnetic field from a coil penetrates the conductor, it generates eddy current, okay, parallel to the surface of the part and at right angles to the direction of applied field. So the frequency of eddy current flow is the same as the electromagnetic field. So what do you think is true or false? So I think it's true. True. Answer is A in this case. Now impedance is the total opposition to the flow of current represented, okay, by the combined effect of resistance, so inductance and capacitance of a circuit. So what do you think? It's true or false? It's true. Answer is true in this case. Now these are the references, okay, which you should refer and increase your knowledge in this topic. See, when you refer these references, obviously these will have a large amount of information. Okay, so based upon the understanding that you have got from this lecture, you should try to increase your knowledge in uh, through these references also. Moreover, these references will also have some, you can say, extra diagrams, which will also give you more knowledge. Okay, so thank you all. Thank you all.